So, welcome everybody to our sponsor spotlight. We have Jeremy Latriano here with 475 High Performance Building Supply. They have been a sponsor of Build Green CT since we merged a few years ago and have been a longtime sponsor of Connecticut Passive House. So, we're always thankful for their involvement and partnership. Jeremy is also very involved in Build Green CT. He leads the emerging professionals community and hosts basically monthly roundtables featuring guests to talk about their role in the sustainability field and how they got there. It's really interesting. I'll let Jeremy introduce our next one. I will put a link for that in the chat as well. For anybody who may be new to Build Green CT, welcome. And we hope you'll consider joining us as a member. There's a link in the chat where you can learn about member perks. And I also want to flag our next webinar, which is on March 19th. It's an introduction to the Living Building Challenge, which is presented by our board member, Melissa Copps, who will also be sort of relaunching the Living Building community with Build Green CT. So we're excited to get that going. All right, Jeremy, please take it away and don't forget to mention career conversations.
Yeah, absolutely. And I believe our next is scheduled for March 26th or the 25th?
Yep,
26th. Okay. So
26th, I
yes,
think. Yep.
thank you for the warm introduction, Sarah. As Sarah mentioned, I do volunteer with Build Green CT as the chair of the emerging professionals community. Our my major effort, I guess, since joining in that role around this time last year has been the establishment of this career conversation series, which is a monthly interview with a professional in the green building sector, ideally someone from Connecticut in most cases, and so far all of our guests have been. Trying to bring in professionals from different lines of work, different industries, not only architecture and engineering, but showing that the green building sector in general is open to people of different experiences and backgrounds, and providing some demonstration and precedent for how you can find your way into a career in sustainable construction, sustainable buildings. So yes, next event is March 26th at 5 p.m. You'll see some advertisements, promos for that event in our upcoming newsletters, Build Green CT's upcoming newsletters. And it is intended for emerging professionals, but really open to all. I think the conversations are really interesting in general. A lot to be learned from these professionals that we speak with. Our next event, we'll be interviewing Bruce Becker, a well-established architect and developer with roots and a practice in the New Haven area, maybe most famously known recently for his development and design of the Hotel Marcel Pass certified hotel in New Haven, just off of 95. So really excited for that one. I think it should be a really great conversation. I'm excited to learn more about how he kind of moved to where he is today. Today, I'm going to be talking about high performance roof daylighting. As Sarah mentioned, I work for 475 High Performance Building Supply. A little bit about myself. I've been with 475 for about 8 years. Most of that time, I've been within our daylight department, specializing in our fenestration products, which previously had included windows and doors, but at this time only include skylights. So today I'm here to talk about skylights specifically and how they can be utilized effectively in high performance buildings. We'll talk a little bit about what a high performance building is, at least in brief, and some of the principles that are important to our company in that regard. In addition to being a product consultant, I'm also a team manager. The Daylight team consists of myself, Delia, and Steve, and we are the primary contacts for all of the Skylight products that 475 supplies. So if you are interested in getting an estimate or consultation on a project that you're working on, feel free to get in touch with me, and I'll make sure you get in touch with the right person there. So this is an AIA accredited presentation. So if you are interested in receiving credits, you can go ahead and take out your phone now, scan this QR code on the right side of your screen. That will bring you to a Google survey, which you can enter your information as well as the provider and course numbers here on the left to ensure that we will get you your AIA credits for your participation. I'll give you guys a minute with that. And then I can also pull it up again at the end. of the presentation. And Sarah, can you just let me know if there's any questions in the chat as we move along? Thank you. Okay, so I'm going to dive in here. Again, if there's any need to view the slide again, I can bring it up at the end of my presentation to make sure you get all your info entered there. Just drop a message in the chat or give me a shout there at the end. So yes, today's presentation is titled High Performance Roof Daylighting. I really don't like this term, roof daylighting. I think it's sort of unnecessarily obscure. But it does do a nice job of sort of describing a few different product groups, which kind of go beyond just simple skylights, so to speak. But when we do talk about roof daylighting, we're talking about slope glazing or glazing on the roof. So that includes skylights, roof access skylights or hatches, as well as glass roofs and more extensive architectural elements. And today we want to talk about how we can integrate and design for skylights effectively in buildings that are aiming for high performance or energy efficiency and optimization of the enclosure via airtightness, thermal control. So usually I'd like to start the presentation off with uh, the question shown here, what is high performance? And just get a sense in the room of what qualities people expect, what characteristics people expect from high performance buildings. I think just given the audience here, I'll probably spare you guys having to turn on your microphones and just kind of give you an idea of some of the things that 475 holds important or that we expect when it comes to quote unquote high performance buildings. So some of the characteristics that we see as benefits or things that are expected from high performance buildings are shown here on the left. The one that is probably most commonly associated is energy efficiency. When we optimize the enclosure, we minimize heat transfer. And when we minimize heat transfer, we can reduce our heating and cooling demand significantly and thereby reduce the carbon footprint of our buildings. What also comes along with a high performance building and enclosure is excellent or exceptional comfort. When we have continuous insulation and airtightness, we reduce drafts, we reduce cold spots, and for that reason, these buildings are consistently heated and very comfortable. In addition, these buildings are very healthy, particularly because they're airtight and they don't allow airflow through the enclosure, so that any air they bring in can be carefully filtered. In addition, high performance buildings we expect to have continuous heat recovery ventilation, and so they're constantly exhausting stale air. So very high indoor air quality and generally supporting good health. These buildings are very resilient in that they excellently manage air, water, vapor, and thermal control. They provide excellent protection for the structure and the control layers. And so there's less need to maintain or repair those elements over time. This one may be a little controversial. Affordable. We like to think that high performance buildings can be affordable, particularly airtightness, which is the most effective way to reduce heating demands in the buildings that we design. It can be implemented in most projects for a relatively low additional cost. So that's one measure that we can take to implement high performance without necessarily breaking the bottom line. But depending on what extent we're going to, that affordability, maybe more or less. And then beautiful. This is an important one. I think that often, particularly passive house buildings, the expectation in the design world is that they are limiting how architects can design. And I think it's important to remember that when it comes to passive house, it can be applied to any building type, really any structure or design or geometry. Similarly, high performance can be applied regardless of or without design restraints. And for that reason, these buildings can also be beautiful. So there are several components listed here that are responsible for creating the qualities of high performance buildings that I just listed. Today, I want to focus on the robust enclosure and quality daylighting as the two main components that we'll be presenting on. So first, looking at the robust enclosure, again, this is somewhat fundamental, so just bear with me as I build the foundation, and then from there we can look at some more specific and interesting concepts. But first, talking about the robust enclosure. So we talk about a robust enclosure, we talk about an enclosure that mitigates heat transfer, heat gains, and heat losses. We want to reach a point in our building where our energy is balanced, meaning that our total heat gains are roughly equal to our total heat losses. generally speaking, in most climates, particularly in Connecticut and where I am in New York, um, our total heat losses in the winter are going to exceed our total heat gains, and that's why we have mechanically generated heat to supplement our heat gains, which otherwise come from the sun or from internal gains, such as our body heat or machinery, computers, electronics in our buildings. But yes, generally we're trying to reach this point where total heat gains equals total heat losses. And if we're mitigating heat gains and heat losses by creating excellent airtightness and insulation in our enclosure, then that becomes much easier. So what does a robust enclosure look like? We at 475 like to reference Joe Strubrick's perfect wall, which you guys might be familiar with, shown here on the left. Conceptual diagram of what every element of our enclosure should provide on the left as a wall, and then on the right shown as a slab or a roof. Essentially, the three main categories of the perfect wall are the exterior cladding, the interior structure, and then also the control layers. And looking a little bit closer at those control layers, we can break them into four categories in the order of importance. They're water control. Water control being the most important because if our buildings can't hold water, they're not doing their most fundamental job, and they really aren't going to be inhabitable or usable, particularly in the long term. Secondly, we have air control. Air control, as I mentioned early on, has a disproportionate effect on energy usage, particularly for heating and cooling. So when we do have high levels of air control, we are going to be reducing our heating and cooling demand most effectively. We'll also be eliminating cold spots. We'll be eliminating a lot of moisture movement. And so air control really provides a lot of benefits. And that's why we have it listed second in order of importance. Vapor control, we're not going to talk about too much today, but vapor being airborne moisture that moves through our assembly and how we manage that moisture and allow it in our recommendation to diffuse passively through our structure. And then thermal control, insulation, how we manage heat transfer via conduction or through the material itself. So if we look at these control layers in practice, we might have a wall assembly such as what is shown on the right. A sort of best practice design technique that our company really advocates for is that early in the design process, you go around the full enclosure, you mark the water control layer in one color, you mark the air control layer in another. Here we can see our water control on the interior face of our masonry, and then our air control on the interior face of our insulation layer just outboard of our interior finish. So these same techniques can be used when designing for air control and water control, and then also thermal control in our fenestration. As mentioned, vapor control not going to be discussed so much today because generally fenestration is going to be vapor tight. We don't really have to consider how vapor moves through our windows, doors, and skylights. However, we do need to consider how our windows, doors, and skylights control air and water, as well as provide thermal continuity, and then how we integrate or ensure continuity between water, air, and thermal control in our fenestration to the surrounding enclosure. And I guess just to back up a little bit, one thing that is really unique about skylights, windows, etc., is that they're really one of the only elements or components in our enclosure that's going to be providing all of our control layers. So in this case, our window is expected to be airtight. It's providing air control. It's expected obviously to be watertight, providing water control. And then in a high performance building, it's expected to be thermally continuous or provide exceptionally low U values. And so it'll also be providing thermal control over the penetration that it's installed within. So it's really critical that we, when designing for high performance fenestration at a penetration, that we are considering how we'll be connecting the air, water, and thermal control in the enclosure to the fenestration element, which is then providing those control layers over the penetration. So for a window, this is a section drawing of one method that we can use to achieve continuity of our control layers. Here you can see we've circled particularly the connections between our air control on the wall and our air control on the window. And we have, in this case, it looks like designated airtight tape to be used from this interior membrane to this window assembly. At the exterior, very similarly, we have our WRB or maybe a water or liquid applied membrane above at the exterior of our wall assembly and then also above our window at the header. And we're wrapping that material down into the opening and then taping from the window to that material. I'm going to focus mainly on water control and air control for the next few slides, and then I'll get into thermal control a little bit. But let's look at how these principles of water and air control can apply to a skylight assembly. So here we show a high performance skylight assembly. I can tell you it's high performance because we see it has triple layer glazing. There's a insulated frame, and then it's prefabricated or mounted on this insulated curb. So we can say with relatively high confidence, based on just the section drawing, that this skylight is probably providing good or exceptional thermal performance. In the case of a high performance building, we can kind of assume again that our skylight in this case is going to be providing water control and air control. So we want to be considering how we're making those connections from the roof to the skylight. In this case, flat roof assembly. So outboard of our exterior insulation, we have a roofing membrane, and because of the skylight assembly has this insulated curb, we can simply run our roofing membrane from the exterior of the roof right up to the side of the curb and terminate it into that side of the curb. And then again, assuming the skylight assembly is watertight, we've done a nice job of ensuring continuity between the structure and the fenestration. Similarly, at the interior, we have our interior air control membrane. We wrap it up into our light well, into our roof opening, and then we can, again, tape it using an airtight tape to the curb. And then, assuming that we've done our job and specified an airtight skylight assembly, we can be assured that that skylight will be continuously airtight to the surrounding structure. This insulated curb or an insulated curb that one will build on site also allows for really great thermal continuity as we can simply run our exterior roof insulation into the side of the curb, sort of embedding that curb in that insulation and then mitigating any thermal bridging or heat transfer that might occur between the curb and the roof itself. So I want to talk a little bit about designing for thermal control specifically now, a little segue there for you. Before I do, are there any questions?
I don't see any.
Cool. Let's keep it rolling then.
Yep.
So how do you optimize thermal control around window, door, and specifically skylight penetrations? Let's talk first about some product considerations for designing for thermal control. The first one is thermal values. Pretty obvious. We need to ensure that we are specifying and installing skylight assemblies that are thermally continuous. This means not only that they have a low UG value and ideally triple layer glazing, but they also have a low U value for the frame, a thermally broken or continuously insulated frame, and that they have what we like to call warm edge spacer or an insulating element between the glass fields that'll prevent heat transfer or thermal bridging between the frame and the glass. So these U values of each component can be combined as a weighted average to get a U value of the full assembly, and that's really the U value that we want to be considering when we are selecting a skylight. So what would a thermally continuous skylight look like in practice? We saw a section drawing of one previously. Here we see a rendering of a very similar assembly. Again, we have triple layer insulated glazing. We have that warm edge spacer that I mentioned. This case is Super Spacer, which is just a brand of warm edge spacer that has exceptionally low psi values or linear um, linear thermal protection. We have in this case an aluminum frame and it has been continuously insulated, so there's not really any opportunity or any conductive materials penetrating an insulation layer, and we can assume that there'll be minimal heat transfer at that location. And then again, we see this skylight has been prefabricated on this insulated curb with foam core insulation or foam insulation core, and so that'll allow us to ensure that the skylight is integrated thermally with the surrounding roof structure and the thermal insulation in that roof structure. So what would a skylight assembly that is not thermally broken look like? It might look something like this assembly we see on the left. This is a thermal model, so we can see these isotherms in different colors, each representing a different temperature range within the skylight assembly. Our warm temperature is shown on the inside in warmer colors, typically red, orange, yellow. Our cooler temperature is shown on the outside in purple and blue. In this case, we can see that as we move through our skylight assembly from curb to skylight, there is a significant thermal bridge at this location where it looks like we have a conductive material, maybe aluminum or some sort of metal, penetrating the full assembly from interior to exterior. And so we can see that this green temperature zone, this green isotherm, is bleeding through the entire assembly, and we're going to have significant heat transfer for that reason at this location. This is a really big problem for skylights because when we see thermal bridging to this extent, we'll have in the winter months very cold interior surfaces as our warm interior air is transferred outward through this conductive thermal bridge. And when we have cold interior surface temperatures due to thermal bridging, we can see condensation occur, particularly again in the winter as we have very warm, moist interior air spending a lot of time indoors, showering, cooking, cleaning, breathing, that warm, moist interior air will rise into our skylight opening. It'll come into contact with the cold interior surface created by thermal bridging, and then it'll condense and it'll, in some cases, drip down into the interior. Often perceived as a leak, but more often condensation. Many skylight assemblies are recognizing that they're not thermally broken and they're not planning to prevent condensation due to thermal bridging at all. Instead, they just design their skylights with an interior gutter and a weep hole. And as condensation occurs, it's collected in that gutter and then whipped to the exterior. Obviously, that's not an option for high performance buildings, as not only is our thermal control in the enclosure compromised, but our air control is as well because of that weep hole. In addition, those weep holes can often become clogged over time, leading to the gutter overflowing and again, potentially spilling to the interior, which can often damage interiors or be, again, perceived as a leak. So now we'll look at some design considerations for designing for thermal control. The main principle when we are designing for thermal continuity between a skylight and a surrounding roof assembly is that we want to be aligning the thermally continuous fenestration or skylight with the thermal control layer in the roof. So we saw this previously when we had our insulated curb embedded in the exterior insulation of the roof. We had the insulation thermal control layer in alignment with the thermally continuous skylight. The same principle applies to windows. I think it's a little bit easier to demonstrate at first how thermal control is achieved in a window. In this case, we're going to make a couple of assumptions in this wall section. With a window penetration, we're going to assume one, that the window is thermally continuous, minimizing heat transfer through its assembly, and that the thermal control layer in the wall assembly is centered. So ideally, to design for thermal continuity, we want to be ensuring that our window is installed in alignment with the insulation in our wall assembly, which, as we said, is centered. So on uh, um, in the thermal models we see here on the left and the right, we can see that our window is installed at the exterior and the interior respectively of the wall penetration. And so we're out of alignment with the insulation in the wall. For this reason, we will see heat transfer sort of bypass our thermal control layer as it moves between the window assembly and the wall insulation. And again, we could see issues with particularly cold surface temperatures at the interior corners of our window, which could create cold spots or discomfort, as well as potentially condensation. In this center image, we've aligned the window with the thermal control in the wall, and so we've really mostly eliminated any thermal bridging that is occurring around the window or through the wall. And that's indicated here by the fact that our interior surface temperatures, shown in the red isotherm, are relatively continuous. We don't see any bridging or kinking of colors, any colors that sort of bleed through the assembly. Our cold temps are maintained at the exterior, and our warm temps are maintained at the interior because we have a thermally continuous window aligned with insulation in our wall assembly. So again, same principle applies to skylights. Here we have just a thermal model of the sort of skylight assembly we looked at previously. In this case, we have that insulated curb that we discussed. And for that reason, when we embed that insulated curb in the exterior roof insulation of the roof, we're going to have really nice isotherms without thermal bridging between the skylight and the roof assembly. We've taken care of the two main principles. First, the product consideration of utilizing a thermally continuous skylight solution, and then the design consideration of aligning that skylight with the thermal control layer in the roof. So when we are considering thermal control, we know it's important because of energy efficiency. It's also important because it's a comfort driver. We talked earlier about high performance buildings and how comfort is one of the main expectations that we have of high performance buildings. So we talked before about the product consideration um, for utilizing skylights in high performance buildings being utilizing a thermally continuous solution. This is an example of why that's so critical. In this example, we have Nick Grant, who said he was feeling warm in his office despite an interior air temperature of around 23 degrees Celsius, which is a little warm, but roughly room temperature, mid 70s. Despite the fact that he was cooling the air and it was relatively normal interior room temperature, he had this feeling like a radiator was on, so he couldn't really figure out why. He took out this thermal imaging camera and he photographed first this skylight on the left and then these windows on the right. And what he realized was that the interior surface temperatures of the skylight and the windows was much warmer than the interior air temperature. In this image on the left, you can see the interior surface temperature of the window is 37.8, and on the right is 43.2 degrees Celsius, so pushing into the high 80s and 90s for those surface temperatures. What happened here is that these windows, they don't meet the basic principles for a thermally continuous solution that we looked at previously. And so we're seeing significant amount of heat transfer in these summer conditions from the exterior to the interior. When that occurs, the interior surfaces of these windows and skylights become very, very warm. And because we have much warmer surface temperatures than air temperatures, that heat on the surface from the surface of these fenestration elements will radiate inward, and it'll make it feel like, in this case, a radiator was on. So a very simple, or at least, yeah, no, very simple solution here would be utilizing a solution that eliminates that heat transfer or that reduces it significantly so that our interior surface temperatures are more in alignment with our interior air temperatures. And then just looking at that sort of more conceptually, but similarly, here we have an example in winter. So we have exterior temperatures of 6 degrees Fahrenheit. In the building on the left, we have what we would say maybe is a low performing building. Image on the right, more insulation, triple layer glazing, a high performance building. When we have very cold exterior temperatures, again, and our fenestration is not thermally broken, in the winter, we'll have very cool interior surface temps on our fenestration. As our warm conditioned air circulates and comes into contact with those cold interior surface temperatures, it'll sink or it'll cool and then it'll sink and it'll leave behind sort of a vacuum where more warm air will be pulled in, cool and sink. And we'll sort of have this thermal circulation or convective looping that can often feel like a draft, but is actually just due to poor U values in our fenestration. If you live in a older, maybe mid-century, mid-20th century apartment building, you'll often see the radiators installed underneath the windows, which is really one design tool for eliminating this convective looping and ensuring that we are keeping these interior surface temperatures warm by heating them mechanically. Obviously, not a high performance solution to a problem that can be addressed by simply improving the thermal performance of our enclosure and our windows, as shown here on the image on the right. We've upgraded our window, we've reduced the heat transfer through our window and our walls, and for that reason, our interior surface temperatures are much more in alignment with our interior air temperatures, and we won't see that convective looping occurring. So we've talked about the robust enclosure. I want to talk a little bit about quality daylighting. Then we'll get into an energy balance example. And then if we have time at the end, I'll talk a little bit about some of the products that our company supplies. Before I get into quality daylighting as a component of high performance building, are there any questions?
No, I don't see any. Carry on.
Cool. Must be doing a great job explaining things.
You sure are. Yeah.
All right, so let's look at quality daylighting. I love to show this image, which includes two of the children of 475 founder Ken Levinson at their home in Park Slope in Brooklyn, sitting in a windowsill on a day that looks a lot like it could be a day this winter, the amount of snow we've been getting. But we can see here that they are right up against the window. They seem quite comfortable in pajamas with no socks, despite the fact that their temperatures are obviously very wintry, very cold. What we can derive from this image is that we have a high performance window or a window with a low U value that's minimizing heat transfer. And so the interior surface temperatures are consistent with the interior air temperatures. We also can see here that the snow just outside the window hasn't melted yet, indication that we're not losing heat outward and that that snow is not being melted using our mechanically generated heat energy. And so we can assume or see here this is probably a relatively high performance install. I can also speak to this project and can tell you that it certainly is, as this was a NFIT certified renovation. But this is a great example of quality daylighting, a robust enclosure. And also we can see that these children are reading using the natural illumination from the sun. And so we can see that it's also a nice example of quality daylighting. So what is quality daylighting? What are some of the principles that are important or that we consider as a company critical to ensuring that our daylight is quality? Well, the first is a balanced window to wall ratio. An important thing to keep in mind as building and design professionals is that fenestration, windows, doors, and skylights is really always going to have a worse insulating value than the surrounding opaque structure. So our U value in our window, doors, and skylights is generally almost always going to be higher than our walls and our roofs. So we don't want to have too much glazing. Where possible, we want to be very considerate of how much glazing that we're using. We want to be utilizing fewer, bigger window assemblies as compared to more window penetrations that are smaller, as windows generally have lower U values in the glass than the frame. And so having a greater glass to frame ratio will improve the performance of those windows. And we also want to make sure that we're optimizing the uh, contributions that the windows are making to the buildings themselves, both the illumination that they're providing, which will help us to offset our electrical demands, and then also the radiation that they're providing, which will help us to offset our heating demands. In addition, we want to be ensuring, as we discussed, that we're using thermally continuous and airtight fenestration, and that we're utilizing diffusion of natural light or shading to reduce visual and physical discomfort, particularly important in our climate where we have both heating and cooling seasons that we have to design for. Some of the benefits of quality daylighting, improved health and productivity. When we have access to natural light regularly, it reinforces our circadian rhythm. It helps us sleep better at night, keeps us energized during the day. It's been shown that students that have access to natural light perform better on tests. Shoppers with access to natural light in retail locations spend more time in store. Um, Natural light also provides the full spectrum of visible light, and so it's the best way to accurately display colors, materials, or in the case of commercial buildings, maybe foods. So there are definitely aesthetic benefits there for quality daylighting as well. Energy savings, which I'll get into in a little bit. But basically, when we have quality daylighting, we're utilizing radiation effectively. We can use that radiation to offset our heating demand in the heating season in the winter, which is particularly important in heating dominated climates such as ours. It also allows us to reduce our electrical loads as when we get radiation from the sun, we also get illumination. Skylights are specific are particularly, sorry, well suited to provide natural ventilation because of their position on the roof. Particularly in taller buildings, they're well suited to take advantage of the stack effect or the tendency of warm air to rise through our buildings, looking for an escape through the roof or the ceiling. In addition, they can also be used for nighttime flushing in shoulder seasons as we allow warm air held by the building to ventilate outward during the evenings. And then exterior access, particularly relevant urban climates such as Brooklyn, where I am located. Skylights that open, such as the one shown here on the right at 475's office in Brooklyn, to a roof deck can allow us to access exterior environments in ways that might otherwise be possible, and to maybe get more out of our buildings than they could previously offer. So, importance of quality daylighting. I'm going to be getting into a little bit of an energy balance example in a few slides, and so I just want to clarify how windows, doors, skylights, fenestration affects energy balance and can provide energy savings as a benefit. We talked about convection, air transfer, and conduction, heat transfer through material, how we can manage that in a skylight assembly and a skylight installation. We are now going to talk a little about radiation. And the idea in a high performance building, how we want to be using our fenestration is that we want to be providing during the heating season more energy via radiation than we are losing via convection and conduction. And if we're able to achieve that balance, more radiation, radiative heat gain than convective and conductive heat loss, we're actually going to be able to get free heat, so to speak, from the sun, which we can use to offset our heating demand. So more on that in a little bit. For now, I want to talk a little bit about the relationship between windows and skylights. Because skylights are oriented towards the sky, they do capture much more light and heat than windows can. And for this reason, they can easily be 3 to 10 times smaller than windows, depending on their orientation, while still collecting similar amounts of light. In this sort of diagram on the right, we have measured illumination during various different weather conditions in foot candles. We can see that on a direct sunny day, we're getting around 5,000 to 10,000 foot candles from the open sky. But even on a dark, stormy, heavily clouded day, we're still getting around 1,000 foot candles from the sky. And so a skylight, even when conditions are unideal, can provide enough illumination to supplement office work in particular, which generally only requires fewer than 100 foot candles to complete comfortably. So another way that it can positively impact energy savings. Let's talk a little bit about how we can design for solar control. First, via product considerations, in this case, utilizing glass types that allow appropriate amounts of light and heat into the interior, depending on what we are needing in our climate and for our building. So again, sort of a fundamental concept here, but there are a couple different ways that we measure light or the amount of light that a window lets in. There's visual transmittance, which is measurement of how much visible light or illumination we receive through a glass surface. And then we have solar heat gain coefficient, which is measuring how much radiation or solar heat from the sun we receive through that same surface. Generally, for a high performance fenestration assembly or skylight assembly, we want to be considering the visual transmittance to solar heat gain ratio, and we want to be ensuring that as much as possible that ratio is right around 2. When it is around 2, we can be relatively confident that that window has a low E coating and that it is going to reduce solar heat gain while still providing excellent levels of illumination. In a heating climate, it's also important to consider that in general, we want to be using visual transmittance and solar heat gain positively. So we want to be receiving as much light and heat as we can comfortably allow, using transparent glazing combined with orientation considerations as well as shading solutions, so that we can get that heat and that light when we want it and block it in the summer when we don't. So a quick example here of a few different glass types and that ratio that I mentioned previously. On the image on the left, we have clear double glazing, no coating, no tint, allowing light and heat in at roughly the same clip. The ratio between visual transmittance and solar heat gain in this case is going to be right around 1, which is not ideal, not exactly what we're looking for a high performance building because we are getting much more heat and light than we need, and we can have issues then with comfort, glare, and overheating. In this image in the middle, we have added a tint to the window. So now we're blocking light, but we're also blocking heat at roughly the same clip. And so again, ratio is closer to 1. Ideal for comfort and energy efficiency is to have a low emissivity coating, such as shown in the image on the right here, which will allow light and visual transmittance to be maintained at high levels while reducing our solar heat gain, giving us a ratio, excuse me, closer to 2. In addition, because we have again heating and a cooling season in our climate, we need to be considering shading or diffusion of light. And ideally, in a high performance building, we're utilizing shading and diffusion at the exterior of our skylights, which will ensure that we're blocking that heat before it ever has a chance to enter our conditioned space. But interior shading is still well suited to prevent particularly visual discomfort, i.e., glare, and so can be effective as opposed to not using fenestration or not using shading at all. Some options that we have for shading are interior or exterior motorized blinds, which are ideal because we can, again, open them and close them easily depending on the conditions that we are managing. And then we also can consider glazing prints or treatments, things like a fritted glass, such as what we see here, which will reduce light and heat by a consistent clip throughout the year and also provide a different quality of daylight, more of a dappled effect, which could be preferable from a design perspective. So let's look at some design considerations for designing for solar control. And when it comes to designing for solar control, the main consideration that we want to keep in mind is orientation. Nothing, no rocket science here. Just we want to be considering the orientation of our building, how we are orienting it on the lot, where we are locating our windows in relation to where the sun will be at any given time of the year, keeping in mind the sun is higher in the horizon in the summer, lower in the winter, and that it's always in the southern horizon. In the northern hemisphere where we're located. We can also use considerations to thoughtfully design fixed shading elements that will allow us to block light and heat in the summer while allowing that same light and heat to enter when the sun is lower in the winter. When we manage solar control effectively, we are going to reduce glare and overheating, which, similar to thermal asymmetry, is a comfort driver and is going to allow us to improve the comfort of our high performance buildings. So I want to now kind of get towards the end of our presentation. I'm going to go through an energy balance example and just demonstrate briefly how skylights can reduce heating demands in the winter if used effectively. Before I get into this exercise, are there any questions?
Not yet.
Okay, let's take it home. So for this example, we'll be looking at this beautiful rectangular prism of a building, carefully designed in MS Paint. We can see here in our bullet points up top that the building footprint is about 200 foot by 200 foot. We have 36 skylights, 38 inch by 38 inch, represented by these small rectangles at the top of our prism. And then total glass area for these skylights of around 323 square feet. Which is important just to remember that the total glass area, the total surface area of our 36 kayaks is about less than 1% of the overall building envelope. So relatively small percentage overall of our enclosure. So in this example, we're going to look at how these skylights specifically will affect our heating demands in the winter, and then how it'll affect our cooling demands in the summer, and how we can change the impact that these skylights have on heating and cooling demand by changing the attributes that we've discussed in today's presentation. So looking first at energy balance of our building in the winter. A lot of data here. I'll walk you guys through it. We have this table on the bottom of our chart with six different columns. Each of these six columns represents a different skylight type as shown on the y-axis in our chart. So, for example, in this first column, we have a double pane skylight. It's not thermal bridge free. It doesn't have curb insulation, has a relatively high UG value, and a solar heat gain of around 30%. And so in this case, in the winter, because our skylight is not thermally broken, it does not have triple layer glazing, we're going to see a significant amount of heat transfer outward as we generate heat inward or at the interior. Our interior environment is warmer, so heat's going to move through our skylight assemblies outward. So we're going to see in this case, we can see we have it as shown in the blue, significant heat losses, significantly more heat losses through our skylights than we have solar gains via those same skylights. If we go to this second column, we're looking now at a triple pane skylight with a conventional spacer. So we have definitely better performance. We have still no thermal bridge free frame. We don't have any curb insulation. We've reduced the U glass value and we've kept the solar heat gain coefficient the same. So we've reduced our heat losses slightly. Our solar gains are the same as our solar heat gain coefficient hasn't changed. However, our skylights are still responsible for many more heat losses via conductive heat losses than they are receiving solar gains. As we move through these next few examples, we again move to a higher performing skylight, triple pane with better spacer. Now it's thermal bridge free. We're again reducing our heat losses. We move to our advanced component. We have thermal bridge free. Now we have a curb with an insulated curb, which is going to ensure we have really good thermal continuity to the surrounding roof structure. Our U glass value now is 0.13, so we're utilizing a high performance triple layer IGU with a warm edge spacer. Via all these measures, we've been able to reduce our heat losses to a point where they're approximately equal to our solar gains. So in this case, our skylights are net neutral. They don't have any impact on our heating demand. They're not creating additional heating demand or reducing heating demand. Our next step is that in these last two columns, we can increase our solar heat gain coefficient to 50% from 30% while maintaining a high performance assembly or thermally broken assembly and a low U value, UG value. And in doing so, we'll maintain exceptionally low heat losses through our skylights while increasing our solar gains to a point where they are greater than our heat losses, thereby getting what we call free heat from the sun, which we can use to offset our mechanical heating demand. So again, looking through our different columns here, this is the same example. Um, and so that is how skylights can provide the benefit of energy savings in a building when they are selected thoughtfully and designed for with consideration. So I'd just like to, in this last slide or one of these last slides, talk about one code clarification for skylights. Um, One of the questions I often get in my job is if fall through protection or screening is required beneath the skylight. Because I think that the mention in code of fall through protection and screening is somewhat unclear. So I just want to kind of give 475's interpretation of this section of the code, which may come in handy as you're specifying or designing for skylights down the road. Um, so as we can see here, in section 2405.2 of the New York City Building Code, slope glazing shall be any of the following materials, allowable glazing materials, subject to the listed limitations. So for monolithic glazing systems, we can see the materials here. Not such a big consideration for high performance buildings, as generally in high performance buildings, we're using multiple layer glazing systems, at least double, if not triple. Um, but the allowable materials in this case are laminated glass with a PVB interlayer, wired glass, light transmitting plastic materials, etc. Wired glass we often see in New York City, but we don't generally see wired glass in IGUs. What we see more commonly in IGUs is laminated glass with this PVB polyvinyl butyryl interlayer. That laminated glass, when installed at the interior of an IGU, is going to prevent anything that falls through the skylight or through the glass surface from penetrating to the interior. So in our understanding of the code, we believe that that laminated glass is sufficient to eliminate the requirement for screening, despite the fact that the building code does not necessarily refer to laminated glass in the section 2405.3. So we're kind of dealing with some ambiguity and just kind of lending our understanding to what we've seen in the industry. So when submitting drawings to the Department of Buildings for permitting, when including skylights, we recommend including language such as this in the respective construction drawings. Laminate glass in bottom layer with PVB interlayer provides permanent protection against falling glass, no screening required. In our experience, that has been sufficient to avoid conflicts with the code and to ensure that no interior screening is going to obstruct or block our light and heat from our carefully selected skylights. So that brings me to the end of the presentation. We leave you with the same image that we looked at earlier on, an excellent example of quality daylighting. And happy to open it up to any questions or to talk about some of the products that our company offers if that might be of interest as well.
Someone alerted me that the chat had been disabled. So even though I'm sure that no one has questions because you're doing such a fantastic job, but I just want to let everybody know that that is enabled now. So we'll give people some time to um, post some comments, and then maybe you can talk about your products, and hopefully we'll have some input there.
Okay, great. Sorry, I'm just trying to charge my laptop here. I thought it was plugged in, but just having an issue. Give me a minute. Let me just also join my cell phone real quick just in case my laptop dies.
There.
And just let me know, I guess, if anyone needs me to go back to the Google survey at the beginning of the presentation as well, if you still need to enter your info for accreditations.
Sure, that'd be helpful if you're able to multitask.
Cool.
But happy to wait. In the chat, someone asked, what form does screening take?
So screening typically would be an actual structural or um, net or screen, something that is going to anything that falls through the skylight, prevent it from
Mhm.
reaching the interior. So the idea is that if the glass shatters, something falls from the sky, that net won't allow that screen or net won't allow that object or the glass that it's penetrated through to fall all the way through to the interior. Laminated glass, though, does have the same effect, which is why we believe that it can be used as an alternative.
Okay. And excuse me, someone else asked um, that they're interested in commercial skylights. Does 475 have only residential or both?
No, that's a great question. Our skylights, particularly the Lamilux units, are really
And
well.
a terrific segue.
Yes, thank you. Lambo skylights in particular are really well suited for commercial buildings. We definitely see a lot of interest in those skylights, specifically the Lamilux FE, which is we showed a few times in our presentation. Aluminum frame with the insulated curb we discussed, thermally continuous assembly. The FE circular, which has a very similar assembly but in a circular geometry,
Hmm.
we find is really well suited or often requested for commercial and institutional jobs. And then the Lamlux PR60, our glass roof system, which is more customizable, sort of a curtain wall or a knockdown system for the roof. This system is often used on larger glass roof spans, things that you might see over a multifamily building, a hotel, college building, that sort of thing. And it can be provided in a lot of different geometries as well to accommodate different designs.
Great, lots of variety there. I
Yeah, no, the system
particularly
is really
like the
awesome.
the round one. That's
The
neat.
bow roof, yeah. I like that one as well. Haven't done one of those yet.
Someone has asked, can a skylight satisfy emergency egress requirements?
Yes, the skylight can satisfy emergency egress requirements. Are generally those requirements are based on the length and the width of the opening, as well as the clear area within that opening. So as long as the skylight um, meets those requirements, it can be used for an egress window per code.
Ava, thank you for a great job. Um, I I think the the in-person example I've seen of one of your skylights is in the Hotel Marcel stairwells. Is that right?
Yes, it is. Two Lamilux FE units were used on that project in the stairwells specifically. I worked with Bruce directly on that one, and then
Hmm.
a product that we no longer supply, but there's actually some of a solar tube product that we used to
Oh.
offer over, um, so that like the middle of the dumbbell, I guess, because they didn't want to put skylights there. They have some like solar tubes that bring light
Hmm.
into the floor just below.
Do you encounter historic preservation with skylights? I know a lot of historic preservation is concerned with what you see from the street, um, so that probably doesn't apply to skylights that much. But
That's the main
um, yeah.
contributing factor, yes. Because they're generally not visible from the street. They uh, are not going to be considered by landmarks. So, um, if they are visible from the street to some extent, we've seen that requirement come into play, and that we have to consider the height of the assembly and the curb structure, particularly to ensure that they are removed from site as necessary, but not generally not as much of a requirement for skylights as for windows.
Hmm. Did you run into that at Hotel Marcel at all?
No, no, we didn't, which is interesting because it is a flat roof. You can see skylights as you drive past on the highway, but I believe it's more about visibility from the ground level up to a certain distance from the building.
I think only architects and engineers and skylight experts probably notice the skylights on Hotel Marcel as they're speeding by on the highway.
I'm definitely always looking for them.
It's a niche group. Another question, does 475 supply any kind of solar tube anymore? What is the
No,
most
we don't
common
provide.
choice among your customers for residential applications?
No, unfortunately, we don't provide solar tubes anymore. Closest thing we can offer is the circular skylights I mentioned previously, which can serve a similar purpose, but are not quite
A
offering the
tube.
same utility. We do supply though more residential skylights for pitch roof applications through the Fakro system. But I had some slides in here for that, but these skylights here are generally our go-to option for pitch roof applications on residential projects. Again, thermally broken assembly. These skylights, particularly FPP, are well suited for as egress windows, but are also available as fixed or center pivot.
So it's the Fakro and Lamilux that
Fakro and
you,
Lamlux are the two manufacturers we work with. Yeah,
okay,
Germany, Lamlux out of Germany and Fakro out of Poland.
okay. How about lead times and logistics of getting them?
Yeah, so we do stock both some of the Lamlux and some of the Fakro skylights at our warehouses in New Jersey and Connecticut, respectively. So those are available with shorter lead times of a few days to a week. Otherwise, the Fakro skylights as a special order require a lead time of 10 to 12 weeks, and the Lamlux skylights as a special order require a lead time of about 15 weeks. So something to plan for.
So you just zipped through a bunch of fun photos of projects. Can you show those off?
Um, Fortunately, hang on one second. Just having some technical difficulties.
Uh-oh. Now we can't hear you at all.
No
No
apologies.
apologies.
No
So,
worries. Hey man, we've all been there. You're doing a good
I'm
job.
plugged in. I'm just not charging, so my computer is like going into hibernation mode now. But I would be happy to maybe follow up with some of those project examples at a later
Okay,
date.
sure. That'll do. All right. Well, maybe that's technology suggesting that this is a good time to wrap up.
Sounds good.
Um, so on a prior slide, Jeremy had shown his contact information. We'll include that in the program follow-up email, and I'm sure he'd be happy for you to reach out to him directly to answer any questions. So thank you very much, Jeremy, for volunteering your time to give us this presentation, and to 475 for your ongoing partnership with Build Green CT. And
Oh,
I encourage everyone to join his career conversations with Bruce Becker on, what did we say, March 26th. You can find that on the Emerging Professionals community page, which I posted in the link, and we'll include that in the follow-up email as well. So thank you all. Have a great day.
thanks, Sarah. Thanks, everyone.